So, so in this example, we're given a cylinder that has a um, a density that varies linearly with position. So as z increases, the density of our cylinder is increasing. So rho is increasing as z is increasing. All right. So what we're asked to find is we're asked to find where is the center of mass. So we're not finding the center of volume in this situation. We're asked where is our center of mass of our cylinder. So in order to determine the center of mass, so what we're looking for here is we're looking for x bar, y bar, and z bar. All right, for this cylinder. All right. So the first thing you'd want to do in this problem is you want, and this is you should do this for all problems, is you should look for, is there any axes that the rigid body is symmetric about. In this case, the rigid body is symmetric about the y-axis, the z-axis. Right? So since it's symmetric about the z-axis here, we know that the center of mass of our rigid body would be for x bar and for y bar are both going to be equal to 0 meters. All right? There's no way that the location of the x centroid and the y centroid is not going to be equal to 0 meters based off of where the cylinder is located. Right? So the second thing we're going to do is we're going to identify the formula we need to calculate z bar. All right, so identify the formula. So if we look back in our packet, we know that for the center of mass, z bar is going to be equal to the integral from the total length of z, so it goes from 0 meters to 1 meter, times z tilde dm. Alright, and then the denominator of our value would just be equal to 0 meters times 1 meter times the integral of dm, which is just the same thing as the total mass of our system. Alright, so we know that dm is equal to rho dv. Alright, so we can plug that, and we know that, alright, so we need to figure out what the heck is dv, and we were given rho in our problem statement. Alright, so we know that rho is equal to 200 z kilograms per meter cubed. Alright, so we need to figure out what the heck is dv. Alright, so in order to figure out what the heck dv is, we're going to plug in, we need to define our differential element. Alright, so in this case we have a cylinder. So for a cylinder, our differential element is that we're going to say it's going to be equal to a very thin disk. Okay, we know this thin disk is going to have an area on top, and then we know that it's going to have a very, very small thickness, dz. Alright, the thickness is so small that we can say that the density within this element will be the same from the top to the bottom, so that we can say that the density of this element is constant. So to determine the volume, or differential volume of our element, we have to multiply the area times dz. Alright, so we know the area of a cylinder is equal to 2 pi, is equal to pi times r squared. In this case, our radius is equal to 0.5 meters squared. and then dz we'll just leave as dz. So this would be equal, dv would be equal to pi over 4 meters squared times dz. Right. So we can use our value of dm and dv into, and we're going to plug these two into our equation here to solve for z bar. Alright, so the last thing we're going to do is just we're going to evaluate our integral. Alright, so to do that, we'll have z bar would be equal to, and the last thing here is that z tilde in this case is just going to be equal to z. Alright, or the centroid of the element is just equal to the position along the z-axis. So if we plug in all of this, we would get, for the top integral for our z bar equation, we would just be equal to z times dm, where dm is equal to rho, times dv, which is equal to pi over 4 meters squared dz. Alright, the one thing I should have done here is rho we know is equal to 200 z kilograms per meter cubed. So you can add that into that equation as well. And then on the denominator we get 1 meter over 0 meters times rho, I'll plug in rho on the denominator, 200 z kilograms per meter cubed, times pi over 4 meters squared dz. Alright, if we look at this, what we should notice is we can take out a lot of constants here. We can take out 200, and we can take out pi over 4, and then in the denominator we can take out 200 and pi over 4, and if we would be left with, on the numerator we'd be left with z squared dz, and on the denominator we'd be just left with z dz. So our 200s and our pi's over 4 will cancel out, so we're left with z bar would just be equal to the integral of from 0 meter to 1 meter of z squared dz, and the denominator would be left with the integral of 0 to 1 meter z dz. So if we integrate those two, we end up with z cubed over 3 from 1 meter to 0 meters on the top, and then on the denominator we'd be left with z squared over 2 from 1 meter to 0 meters. If we evaluate those two, we would get 1/3 meters cubed minus 0 meters cubed over 1/2 meters squared minus 0 meters squared, or we'd end up with just 2/3 of a meter, or 0.667 meters. Right. So if we look back at our the start of the problem, in order to find the centroid, we first looked at if there was any symmetric axes of symmetry in our system. So we noticed that there was one axis of symmetry on the z-axis. Therefore, we knew that x bar and y bar should be equal to 0. We then identified a formula that could be used to determine z bar for the center of mass. So we knew that z bar would be equal to this equation here. In order to perform our integral, we have to relate our differential mass in terms of a volume. So we need to know the relationship between mass and volume is related by the density. So we were able, since we knew what the density was as a function of z, we could plug it in to our differential element in order to do our integrals. Then the last thing we need to do is we need to define our differential element. So since the only thing so we tried to define everything in terms of z, so we need to make sure that we had defined dz, and then we had defined dv in terms of our z component here. So dv, which is equal to our area times dz for the thickness of a very thin cylinder, or for the volume of a very thin cylinder. And once we had all that, we could just plug dv and dm into our integral for z bar, and then we just hit integrate, and we got our answer. All right, so that concludes how you could determine the center of mass for a 3D object using our integration formula.